As you've seen from chapters 1, 2, and 9 of the Seaborg text, mathematical models of real processes often result in systems of linear ordinary differential equations. Systems of linear ODEs should have analytical solutions, provided we have enough initial conditions. The Laplace transform method is one way to reduce the time required to find a solution to an ODE by converting the ODEs to algebraic equations. Now, you've already studied Laplace transforms in your differential equations course, but you may not have used them very much since you took that class. We're going to use Laplace transforms a lot in this class. In fact, much of what we do for the rest of the semester will be done in the Laplace domain. And in fact, you may remember that finding Laplace transforms is not difficult, but inverting Laplace transforms back to the time domain can be challenging. As we go along, you'll be happy to learn that in fact we don't have to convert things back to the time domain. We can do much of our analysis and design in the Laplace domain where everything is algebraic. In fact, you're going to become so familiar with the Laplace domain that I think by the end of this class you're going to prefer using the Laplace domain to using the time domain when analyzing systems of linear ODEs. Now, the Laplace transform is a linear operation. What that means is when we use the Laplace transform to convert an expression for a function of time into an expression for a function of s, there's a one-to-one correspondence between little f of t and capital F of s for all t greater than 0. Since there's a one-to-one correspondence between little f of t and big F of s, we can also convert back from the Laplace domain back to the time domain. And that conversion back to the time domain will also be unique for all t greater than 0. We say there's a one-to-one correspondence for f of t and f of s when t is greater than 0 because the Laplace transform actually doesn't know anything about the behavior of f for t less than 0. It only accounts for the f of t between t equals 0 and infinity. And because this is a definite integral, of course when we evaluate, all of the t's get replaced with zeros or infinities, so the t's go away and we're left with s as the Laplace domain independent variable. The Laplace domain independent variable s has dimensions of reciprocal time, the same dimension that's used for frequency or for rate. In chapter 3 of the methods text, we're going to review what you already know about Laplace transforms. We'll revisit some Laplace transforms of some common functions, and of course, we'll show the inverse transforms as well and review how to find inverse transforms. Then we'll show how we can use Laplace transforms to solve ordinary differential equations and systems of ODEs. And we'll review some of the key properties of Laplace transforms that we'll use throughout the semester. Then we'll do an example where we consider a chemical process that gives rise to a linear ODE model. Finally, we'll show you how you can use MATLAB to evaluate Laplace and inverse Laplace transforms.